Hi, this is Angela Galloway, and today we are going to be working on 16.3. So this is one of several videos I've had for chapter 16, but I'm trying to split them up so it's not so much all at once. So 16.3 is all about apportionment. Now, before this section, we had been talking about different voting methods, good things about the voting methods and maybe bad things about the voting methods. But in this one, we're getting into something different, talking about apportionment. And so first we just have to figure out, what is apportionment? What does that mean? So if you want to watch this little video here, it's kind of just a little YouTube video that shows how the apportionment works in the House of Representatives, because that's one of the places that the book kind of talks the most about apportionment, because that is something that is happening in real life now, so it makes a little more sense there. But you can watch that little video if you want to. But apportionment in general is just a division or partition of identical, indivisible things according to some plan or proportion. So it doesn't have to have anything to do with government and all that, but we do see it talked about there fairly often because of the House of Representatives using it here in the U.S. So you see here the Constitution requires a census of the population of the U.S. every 10 years, and that the House of Representatives be reapportioned according to the current census data. Since the initial apportionment of the House seats in 1794, only 4 different methods of apportionment have been used. The Hill-Huntington method was introduced in 1942, and that's what we currently still use. So we actually aren't going to go over the Hill-Huntington method because it is a little more mathematically complex. So we won't be talking about that one, but we are going to talk about some of the earlier methods. So we'll be talking about the Hamilton method, Jefferson, and Webster are the 3 methods we will be talking about. So some preliminary steps for apportionment that you're basically going to do with all of your methods there is we want to compute the standard divisor. Okay, and the standard divisor we represent with a D, and it is the total population that we're dealing with divided by the total number of seats. Now seats, when it has this here, this is I think pulled from your book, these equations, the total number of seats is referencing back to the House of Representatives. So you don't always have to be working with the House of Representatives. You could be giving out a certain number of objects or whatever, but this is just the number of items that you're trying to allocate amongst the whole population, whatever it is, whether it's seats or objects or whatever. Compute the standard quota for each state. Again, each state, we're talking about House of Representatives, but it could be for each school or each hospital or each whatever you're allocating things to, okay? Then we're going to compute this standard quota, okay, which we call Q, for each of our states or things that we're allocating our items to. So Q equals the state's population divided by D. So of course D came from up here, right? How many do we get? Okay, so Q is going to tell us how many representatives each state gets, or how many items each place gets, whatever, okay? Now, after we do this, if Q is equal to a whole number, that would be great. Our process would be done, but that is rare. So I'm going to give you first just a simple example where we do get a whole number for Q, and so you can kind of at least understand what's going on here, okay? There are 3 high schools in a certain district. A grant allowed the district to buy 20 computers to distribute amongst the schools. The superintendent wants to use apportionment to correctly distribute the computers. Okay, so if we have 3 high schools and we have 20 computers, what we could do is just divide 20 by 3 and just give those out evenly, right? Now we couldn't give them totally evenly, but let's say we had 21 computers. We could divide by 3 and each school would get 7. So that's one way to give out the computers. However, this superintendent realizes that each school has a different population, right? So it seems like it would be more fair that the bigger schools would get more computers, the smaller schools would get less computers, right? And then that way, each student would have similar access to the computers, right? If there's more students, there's more computers. If there's less students, there's less computers, okay? So we see that school A has 500 students, school B has 300, and school C has 200. So to get our standard divisor, we want to find the total population. So how many students do we have in total? Well, we add that up and we get 1,000. Okay, so our standard divisor would be 1,000 divided by the total number of seats or objects that we have to allocate. So how many computers do we have to give out? Well, 20, right? So 1,000 divided by 20 equals 50. Okay, so this is our standard divisor. So what does the standard divisor mean? Well, in this case, this is what that 50 means. This means we can distribute one computer for every 50 students at a school. Okay, so for every 50 more students you have, you get one more computer, right? So if we do that at each school, that's going to allow it to be more fair to the students at a bigger school and still fair to the students at the smaller school, you know. So this means that for every 50 students, there's one more computer given. So at school A, we would have, we're doing our Q now, right? And this is going to tell us how many computers each school is actually going to get. We take school A's population, 500, and divide by 50, which was the D that we just figured out, and we get 10. So school A is going to get 10 computers. School B, it'd be 300 divided by 50, and we get 6. School C, we have 200 students there, divide by 50, and we get 4. So we add all these together, we did 20 computers, and that's how many we had to start with. So like I said, this is a simple case where when we calculate our Q, they all come out to whole numbers, it all adds up to 20, and that's great. It works out nicely there, so we would be done. The problem is that Q, when we figure it out, is usually not a whole number. We're usually going to get something with decimals in it, okay? And so in that case, we have to decide, well, who gets those remaining seats or those remaining objects? Because do we just give it to the ones that have the biggest decimal? Do we round up the decimals? Do we round down? So there's just different ways we can look at it, okay? And so this was one of the main issues that they ran into when they were doing the House of Representatives, because in theory it sounded good to apportion these seats, but then when they got down to it, you know, they figure out, you know, how many seats should each state get, they weren't coming out to whole numbers. And so then, of course, you know, if you're at a state that says you should get 50.5 seats, you would want to say, well, let's just round that up to 51. But if you're at another state that has 50.2, you're like, well, I want to round mine up to 51 also. You know, how come you get to and I don't, or whatever. So they had to figure out a standard way to deal with those decimals. So when they did that, they came up with all these different methods, and each method that we're going to talk about, eventually they found some issue with it. They found that it either favored small states, favored larger states, didn't work in certain situations, whatever. Okay, so the first one we're going to talk about is the Hamilton method, and this was actually created by Alexander Hamilton. So we're going to hear a lot of names that we've heard of in U.S. history classes. Now this method happens to favor smaller states. Now Hamilton happened to be from a smaller state, so I'm not sure if he created this method and maybe didn't notice the issue because he was from a smaller state, or if he did notice the issue and was just hoping that they would go with it, so his state would maybe get more representation in the House of Representatives. So for this one, we're going to calculate Q like we normally would, like we did on the last problem. But when we do that, we're probably going to get decimals. When we get those decimals, we're going to round Q down to the nearest integer, which basically means just ignore the decimals. So if you have 5.2, it's going to round down to 5. If you have 5.8, it's still going to round down to 5. So everything, we're just going to look at the whole number part. Give any additional seats one at a time until no states are left to the states with the largest fractional parts of the standard quotas, which means the largest decimals. So if you have a 0.8 and somebody else has a 0.6, the 0.8 would get that extra seat instead of the 0.6, okay? So let's do an example and that will make a little more sense. The book club is giving away free books to the English 101 classes. They have 120 books to give. The books are to be given away to randomly selected students in each class. However, the book club wants to apportion the books so that the bigger classes are given more books and each student has an equal chance of being selected to win a book. The class sizes of the 6 English 101 classes are below. So here are different class sizes. So you see some are much bigger than the others, like B is basically double what D is. So in this case, you know, if we had 120 books and we have 6, do I have 6 classes here? Yeah, we have 6 classes. So if we were to just give them out evenly amongst the 6 classes, each class would have gotten 20, right? But that means in class D, you know, a lot of the class, you know, 2/3 of the class is going to get a book, right? But when you go here to class B, only about 1/3 of the class is going to get a book, right? So we want to allocate it or apportion it amongst these so that everyone has an equal chance of getting a book. Okay, so let's add up all these classes here and we get 259 as our total number of students. So we're going to calculate D, our standard divisor. That's what we're always going to do at the beginning. So our standard divisor here is going to be 259 divided by 120, which was our total number of books. And we get 2.1583. So that means for every 2.1583 students, we will give away a free book, okay? Or there's a book for every 2.1583 students. So this is why we usually are not going to come out with nice whole numbers, because this D is most often going to be something with a decimal. Then you're going to divide different numbers by this decimal and get more decimals. So you're not going to see something work out as nicely as our first simple example did. Okay, so we have our class size here. Now we're going to calculate our standard quota. Remember the standard quota is Q. Okay, so looking here, our standard quota, after we've calculated the standard divisor, we're going to calculate the standard quota, and this says for each state. In this case, it'll be for each English class. Okay, so we're going to take each English class's population or size and divide it by D, which is what we calculated in the first step. Okay, so we're going to take 55 and divide by 2.1583 and we get 25.48. Then we do 60 divided by 2.1583 and we get 27.8, okay? And so that's how we're getting these numbers here. We're dividing each class size by D. Now this next step here, this is our what we're doing because it's the Hamilton method. Okay, so this here is done because we're using the Hamilton method, okay? So what we did is going from here to here, we took this number and rounded it down or removed the decimal, however you want to think of it. We went from 25.48 to 25, 27.8 to 27, okay, 19.46 to 19, etc. So you see we get all these, we add them all together, and we see we get 117. So right now we're done, we've rounded down, okay, but using that method we only got 117 books given out, right? But we had 120 to give. So we have 3 books left over that we haven't given out yet. So now it says give any additional seats or items one at a time until no seats are left to the states or to the, in this case, the English classes with the largest fractional parts of the standard quotas, so the largest decimals. So looking back here, when we look at these, which one has the largest decimal? Okay, so the largest decimal here would be 0.8, right? 27.8. So they get 1. We're going to add 1 to their total. So now they get 28 instead of just 27, okay? After 0.8, what's the largest one? Well, this one, right? 17.61. So they get 1 more book. So 17 plus 1, they get 18, right? And we have 3 books left. We've given away 2, so we have 1 more. So the next one would be 25.48, right? 48 is the biggest of the decimals remaining, and so they get plus 1, and so they now get 26 books instead of just 25. Okay, so we'll add all these together and notice that we do get 120. So you always want to check at the end and make sure that you have apportioned all the books or all the items that you have available. Okay, and we get to 120. And so on your homework, you'd probably be putting in these answers. Now you might still be doing all this in the background, but this is probably the answer they're looking for, is how many books are you actually apportioning to each class. Now, Jefferson's method. Jefferson's method happens to favor larger states. Jefferson was in a larger state, so again, you might wonder if that's the reason why this method happened to favor larger states, but we're not really sure totally about that. But for the Jefferson method, we introduced something new that we haven't done yet, and that is the modified divisor and the modified quota. Okay, so when we were doing Hamilton's method, we did the divisor and we calculated the D, we calculated the Q here, and we didn't adjust them at all. Okay, we just used what we got after we divided them. Okay, and then to make up for those decimal parts, we added back the books into whatever we needed, wherever we thought whoever deserved another book or another computer or another seat, whatever. In this one, though, what we're going to do to make that total come out correctly, we're going to change the modified divisor, which will then, of course, change our modified quota. Okay, so the modified quota is going to be equal to the state's population divided by the modified divisor. We're going to round each state's modified quota down to the nearest integer and give each state this integer number of seats. So at this point, when we round them all down and add them up, we're hoping that it should add to the number of items we had to give out. Okay, so this example, CL operates 6 secluded resorts in the Caribbean. They recently purchased 30 new sailboats. Company executives decide to use the Jefferson method to apportion the new boats, basing the apportionment on the number of rooms at each resort. The number of rooms at each location is in the table. So here's our number of rooms. Okay, so that would be like our populations, right? So when we add all these together, we get 2013, which is the total we're using here, okay? We can compute our divisor like we always have at the beginning. We get 2013 divided by 30, okay? 30 is the number of boats that we have to get out. We get 67.21. Okay, and right now I'm just going to erase this because this is what we're going to talk about. I don't want this to confuse you right now. Because you're not going to know what it's talking about. Okay, so we've got this. We figured out D, right? And so now the way we get this here, all of these numbers, Q, remember, is going to be equal to each of the populations. So in this case, we're talking about different resorts, right? So each of the resorts populations here divided by D. Okay, and so that is how we get Q. So we always have to calculate D first so that then we can divide each of our populations by D to get Q. So this is our standard quota here. Now our rounded down Q, so we're going to round down just like we have before, just like we did in the Hamilton method. And so we get 5, 3, 6, 4, 4, 5. We get 27. Okay, so 27. How many items did we have to give out? We had 30, right? So 27 is too small, right? Or not enough. But we're just going to say too small. Now, if a number is too small, like if an answer is too small and you were doing a division problem, that means what you divided by was too big, right? So this was too big. Okay, so that's what you have to determine in this method. When we look at this, we see that this number was too small because we had 30 and we only got 27 apportioned out. So that means the number we divided by was too big. That means giving one boat to every 67.1 rooms was too much. We could give one boat to less than 67.1 rooms, okay? So the next part is probably the hardest part, okay? We have to figure out a modified divisor, okay? There's really no correct method for figuring out the modified divisor or where to start at. Because if this number is too big, I want something smaller than this to divide my number of rooms by, okay? So if 67.1 is too big, that means 67 would be smaller, right? So I could start with 67, or I could go down to 10, or I could go to 20. I mean, you just have to pick a number smaller than 67.1. So really your only guidelines are choose a number between 0 and 67, right? So where do we start? Well, for this one, you want to see how far off are we? We're only 3 off, right? Not a big difference, but also not a real small difference. Like if we were just 1 off, then we wouldn't want to change this very much. Maybe we would just go down to 66 or something and try it. Since we're 3 off, I'm going to try a modified divisor of 60. The reason why these problems can take a little while is because, if you started at 67 and you tried to get your modified Q again, it might still be too small, and then you might have to go lower and keep going lower and lower until you finally got to something that worked. So it's kind of just a trial and error at this point. So what we're doing in this column is we're calculating our MQ, okay? The MQ is our modified quotient, or modified quota, I'm sorry. And the only reason it's called modified quota is because we chose a modified divisor to create this number, okay? So my new modified divisor is 60. I just chose this randomly out of the air, okay? So 60, I'm just guessing. I'm going to see if that works because 60 is less than 67.1, right? I want a modified divisor that's smaller than 67.1. So the way we're going to see if this works is we're going to go back, calculate our MQs by going to each of these populations and dividing by 60 now instead of dividing by 67.1. Okay, so this number I get by doing 345 divided by 60. I get 5.75. 234 divided by 60. I get 3.9. Okay, and so that's how I'm getting these numbers. Then the last step says round each state's modified quota down to the nearest integer, the same way we did with the Hamilton method. So rounding this down, I get 5, 3, 7, 5, 4, and 6. I add all those together and I get 30. So that works, right? Now the other good thing about this, yes, you do have to guess about which modified divisor to use. However, this won't be the only one that works. Like you might be able to use 61 or 60.5 or 59.8 or what, there's probably going to be a lot of different options that you could use. I usually, if I can, go for a whole number because that's just always easier to divide by than trying to do something with a decimal. So if possible, I try to grab a whole number. Now, if I'd done this and it had added up to 29, then that still would be too small, and I would know my modified divisor was too big, and so I need to make it smaller. If my number had added up to 32, that's too big, right? Because I only have 30. 32 is too big. If this is too big, my modified divisor is too small, so I need to make it bigger. Okay, so that's the hardest part with these last two methods. It's just that there's some trial and error in there that you have to get used to, when you're learning these methods. The Webster method is similar to the Jefferson method, but the difference is in the Jefferson method, when we went from this part to this part, we rounded down the MQs, right? We basically ignored the decimals and just looked at the whole numbers. In the Webster method, when we go from the MQ to actually apportioning the numbers, we're going to round based on the traditional rules of rounding. So if it's 0.5 or greater, we round up. If it's less than 0.5, we round down. So that makes it can make it a little more difficult when we are doing that, because we might have to adjust our modified divisor a few times. But we'll show an example here, and hopefully it'll make some sense. But this is definitely the hardest method here. Oh, sorry. 40 nurses have volunteered to help at 5 hospitals treating the victims of an earthquake in a mountainous region of Mexico. The Mexican government decides to apportion the nurses based on the number of beds at each hospital. So we have 40 nurses. That's what we're going to apportion. These are our different populations, so the number of beds at the hospitals. So again, I'm going to erase some of this stuff here. Oops. Go back in, write that in. Okay, so I usually go ahead and lay mine out kind of in this chart form, and you're kind of going to see that, and some of your homework might be set up that way. So this is usually just how I do it. You don't necessarily have to do it like this, but that just helps me to kind of remember where I am, and so I don't get all my numbers just confused. So it makes it a little easier if I write it like this. So here's each of my hospitals and the number of beds with each of those hospitals. This is the total number of beds. Okay, so we added all these up and got to 1721. So the first thing I do in all of these, I find the standard divisor. So I'm going to do 1721 divided by 40. And so that gives me 43.025. So that means for every about 43 beds, a hospital is going to get another nurse apportioned to them. Okay. Now take each of these beds, and we want to see how many nurses each of these hospitals is going to get. So we do 137 divided by 43.025, we get 3.184. 237 divided by that, we get 5.508. Okay? All right, now the rounded Q here, okay, like we've been doing, on the other ones when we did the rounded Q, we dropped the decimal, right? We rounded down. This method, though, we're going to round based on how we would normally round. If it's 0.5 or greater, round up. If it's less than 0.5, round down. So 3.184 comes to 3. 5.5 comes to 6, 7.8 is 8, 10.5 is 11, and 12.8 is 13. So I add all these up and I get 40. So is 40 too big or too small? I mean 41. I'm sorry, we get 41. So 41 is too big, right? It's too big because we only have 40 nurses, right? So if we give out 41, somebody's not getting one of those nurses that we had apportioned to them. So if this is too big, that means our standard divisor is too small, right? Okay. So if it's too small, I need to make it bigger. When you have to make it bigger, then you have an even bigger challenge, because now making it bigger, I'm like, okay, so I need a number that's greater than 43.025. but there's really no upper bound, right? So do I make my divisor 100 or 80 or 50, or how far do I have to go? Well, like I said before, look at how far off we are. We're only off by one, right? We have 40 nurses. Right now, I'm apportioning that we have 41. So you're only one off. So you don't need to change this a whole lot. Okay, so what I tried first was, and so I was showing my class on this was that sometimes you're going to have to try several divisors, modified divisors, before you get the right one, and that's okay. That's going to happen sometimes, and the more you do it, the better you'll get at guessing what they are. Okay, so I went from this to 44. So I said, well, 43.025 is too small. I need to make it bigger. So I'm going to try the modified divisor of 44. All right. So if I do that, I'm going to divide each of these by 44 now. So 137 divided by 44 is 3.11. 237 divided by 44 is 5.39. Okay, so I did all these. Now I do my rounded MQ. So notice that each of these is going to this. I just have multiple columns because I had to try different modified divisors. So 3.11 goes down to 3, 5.3 goes to 5, 7.6 goes to 8, 10.34 goes to 10, 12.6 goes to 13. Okay, I add all those up and I get 39. So now I'm too small, right? Now 39 is less than what I have. So this is too small. That means my modified divisor that I chose was too big. But now I have a pretty good idea of what the modified divisor should be, right? Because this was too small, this was too big. So my number needs to be between 43.025 and 44, right? So it shows me that I didn't really have to change it very much to get a big change in my sum, right? So I'm going to try this time 43.3. Again, these are just guesses, okay? They're just guesses based on, this and based on what I know about division and all that kind of stuff. Okay, so you could try 43.2 or 43.4 or 43.5. Some of those might work and some of them might not. This one is going to work for us. So we'll do 137 divided by 43.3. I get 3.16. Okay, so that's how I'm doing that there. So now, once I've gotten this, 3.16 goes to 3, this goes to 5, this goes to 8. So all those are the same as before. But now this goes to 10.5, which gets me up to 11. And this still stays at 13. So now I've added one more here, which adds one more to my sum down here. So I'm now at 40, which is my answer. So on your homework, they'll just be asking for this last column here probably. But you may have had to do this, 3 or 4 times, but the homework isn't really going to see or work on that. They're more concerned, they just want to know if you got these numbers right, then you did all this other stuff right. Okay? Okay, so 16.4, I just kind of go over this real quick. I don't necessarily really expect y'all to know all this stuff or memorize it or anything. We actually don't even have homework on 16.4. But the reason why I go over this is kind of like why I go over section 16.2 when we talk about there's no perfect voting method. The same thing here that there may not really be a perfect apportionment method. So what we see in these different paradoxes and these rules is that some methods may be good in some cases and bad in other cases, or some things may come up that you thought a method was doing really good until you had some kind of weird paradox or whatever come up and you realize, oh wait, that doesn't really work in that situation. So if you want to read a little bit about this in 16.4, that's what it's basically about, is just looking at how there's no perfect apportionment. So this shows here, kind of like we did with the different voting methods, how some of them worked with the majority criterion, some of them didn't, some of them violated the Condorcet candidate, and all that stuff. So we're looking at and these different paradoxes in the rules, if they're satisfied or not satisfied and all that. Okay, so that's what section 16.4 is about. Again, you don't really have homework on that, but if you want to just kind of read through it, it's just kind of interesting, some of the paradoxes they ran into as they were trying to figure out the perfect way to apportion. And those paradoxes occurred when we were talking about the House of Representatives. So you might want to look in your book on 16.4. Okay, so that finishes chapter 16, which is unit 1 for our Math 146 class. So if you have any questions, please feel free to email me at angela.galloway@kctcs.edu, or of course you can always click the Ask My Instructor button as you're working on a homework problem, so that you can contact me and let me know that you're having some issues with some of those problems. If you need anything else, please just get back with me. Thanks.